Please read from the screen purpose for the day. Sure. Let's see here. Let's go on to Madison. Relevant. Zach. Success. Sierra. I took my family to the ocean a few years ago, and I would have to say that I was very concerned about my young kids at the time being swept out to sea because of riptides and things like that. And I wasn't terribly aware of the area, and I didn't know what the danger was. If I had known some of this information, I wouldn't have been so concerned. But I've worked up this lesson since that time. Today's grades, we're going to have a video on tides where you learn just about everything that I'm going to teach you is through this video. And you're going to make a project, a poster of some sort, and you're going to post it on the wall like those folks did over there. Next quiz grades are the next lesson. Our next lesson will be the vocab quiz tomorrow. Concept quiz after that. Main ideas. Romeo, please read paragraph number 1. Romeo, paragraph number 1, please. This is what you guys should have learned yesterday in your little project. The continental rise is the pile of sediments that have come from the continental shelf and the continental slope. Mr. Matthews, from the screen, can you read number 2?
The vast flat areas of the ocean floor are called submerged. They are very flat with the very deep layers of sediment.
Alejandra, number 3. Please put away your food. Number 4. Let's see here. Mr. Connor? Okay. Daryl? Please put away your food. Thank you. Number 5. If a volcano is underwater, it may grow to reach the surface and be an island. Until it reaches the surface, it's called a seamount. Sometimes islands are eroded by waves, and then the crust moves to put the eroded island underwater. This forms a flat-top mountain or seamount called a guyot. We're going to skip page 39 for now, and also page 40. To speed things up, we're going to just review again yesterday's project by looking at this diagram. The abyssal plain. Please look at the diagram. Which one is the abyssal plain? Right down there. No. The abyssal plain is the flat area at the bottom of the ocean. It's going to be G, this area right here, this flatness. The continental rise. Actually, I'm going to skip that for now. Let's do the continental shelf next. The continental shelf is this flat area way up high. Just like a shelf in your bedroom is a flat thing way up high on the wall, the continental shelf is a flat area way up high next to the continent. So that's going to be section A. And then there's the edge of it. Here's letter B for the edge. That is called the continental slope, B. It looks like it's really super steep there, like mountain climbing kind of steepness, but that's a little bit misleading. Think about a really steep hill on an interstate. Those aren't super steep, but it's something that you would not want to ride your bike up, for instance. It might be a little bit more of a challenge than you're wanting to do. That's the steepness of the continental slope. And things do tumble down there. They tumble down and pile up at the bottom, and the bottom then is not quite as steep as the slope, but it's still not flat. That is what we call the continental rise, C. So the three areas next to the continents have the continental aspect of their name. Trench is going to be H. Those are the deepest spots of the ocean. And I'm going to go to number 7 next. The mid-ocean ridge is letter D. These are very much related because they are formed by the same action. The action is that of the mantle. The mantle has those currents in it, remember, and those currents go up and out and back down. So as these currents go up, they push these mountain ridges up. As these currents go outwards, they pull the crust apart, making the deep rift valley in between. That's the mid-ocean ridge and the mid-ocean rift valley. And then when they come on down, that's when they form this trench. So both the ridges and the trenches are formed by these convection currents. Volcanoes can occur underwater, and if they're really small and not reach the surface, they're called seamounts, like this one right here. And I covered up the letter there. Was that letter F? I believe letter F. When they grow tall enough to reach the surface, then they're going to make an island, and that would be letter E. Next page. Let's watch this video.
He would have been right. You might just think, if Shakespeare had been an astronomer, he'd have said that there is a tide in the affairs of the universe, and on such a full sea are we now afloat. He would have been right. You might just think of tides as the ocean going in and out every day, but in fact, what astronomers call tides are a subtle but inexorable force that have literally shaped most objects in the universe. And to understand tides, we start with gravity. Gravity is a force, and it weakens with distance. An important thing to note is that we measure gravity from the center of mass of an object, not its surface. One way to think of the center of mass of an object is the average position in an object of all its mass. For an evenly distributed sphere, that's its center. Right now, unless you're an astronaut, you're about 6,400 kilometers from the center of the Earth. If you stand up, your head is a couple of meters farther away from the Earth's center than your feet. Since gravity weakens with distance, the force of Earth's gravity on your head is an eensy-weensy bit less than it is on your feet. How much less? A mere 0.00005%.
Okay, so there we've done questions 1 and 2. Gravity gets weaker with bigger distance. A for number 1. Number 2, the gravity on your head is 0.00005% less than the gravity at your feet. Number 3, the change in gravity's strength as you move a greater distance away is called blank. Be listening for that in the next few moments.
And that's way too small for you ever to notice. But what if you were taller? Well, the taller you are, the farther your head is from the Earth's center and the weaker force it will feel. If you were, say, about 300 kilometers tall, the force of gravity would drop by about 10% at your head. That probably would be enough to notice if you weren't dying from asphyxiation and, being 300 kilometers tall. This change in the force of gravity over distance is what astronomers call the tidal force. When you have a massive object affecting another object with its gravity, its tidal force depends on several factors. For one thing, it depends on how strong the gravity is from the first object. The stronger the force of gravity, the stronger the tidal force will be on the affected object. It also depends on how wide the affected object is. The wider it is, the more the force of gravity from the first object changes across it, and the bigger the tidal force. Finally, it depends on how far the affected object is from the first object. The farther away the affected object is, the lower the tidal force will be.
So we've done now 3 and 4. Number 3, the change in gravity strength as you move a greater distance is called the tidal force. And number 4, the tidal force depends on the size of the object, the width of the object, and the distance of the objects. Okay. Numbers 5 and 6, read those to anticipate what's coming up.
Tides depend on gravity, and if gravity is weaker, so is the tidal force. The overall effect of the tidal force is to stretch an object. You're applying a stronger force on one end than you are on the other, so you're pulling harder on one end. That'll stretch it. And this is where tidal forces become very important. Look at the moon. It has gravity, but much less than the Earth because it's less massive. It's 380,000 kilometers away, so the gravitational force it has on you is pretty small. And you're pretty small compared to that distance, just a couple of meters long from head to feet. But the Earth is big. It's nearly 13,000 kilometers across. That means the side of the Earth facing the moon is about 13,000 kilometers closer to the moon than the other side of the Earth. This is a pretty big distance, enough for tides to become important. The side of the Earth facing the moon is pulled harder by the moon than the other side of the Earth, so the Earth stretches. It becomes ever so slightly football-shaped, like a sphere with two bulges, one pointing toward the moon and one pointing away. This is probably the weirdest thing about tidal forces. You might expect only one bulge on the side of the Earth facing the moon. But remember, we measure gravity from the centers of objects. The side of the Earth facing the moon feels a stronger pull toward the moon than the Earth's center, so it's pulled away from the center. But the side facing away from the moon feels a weaker force toward the moon than the Earth's center. This means the center of the Earth is being pulled away from the far side. This is exactly the same as if the far side is being pulled away from the center, and that's why you get two bulges on opposite sides of the Earth. The tidal...
We've now covered 1 through 7. Look at number 8 now.
Force is therefore strongest on the sides of the Earth facing toward and away from the moon, and weakest halfway in between them on each side. A lot of the Earth is covered in water, and water responds to this changing force, this stretching. The water bulges up where the tidal force is strongest on opposite sides of the Earth. If there's a beach on one of those spots, the water will cover it, and we say it's high tide. If a beach is where the tidal force is low, the water's been pulled away from it, and it's low tide. But wait a second, the Earth is spinning. If you're on a part of the Earth facing the moon, you're at high tide. 6 hours later, a quarter of a day, the Earth's rotation has swept you around to the spot where it's low tide. 6 hours after that, you're at high tide again, and then another 6 hours later, you're at low tide for the second time that day. Finally,
we've now seen up to 11. Read number 12 to anticipate.
a day after you started, you're back at high tide once more. And that's why we have 2 high tides and 2 low tides every day. Very generally speaking, the ocean tide causes the sea level to rise and fall by a meter or 2 every day. Incidentally, the solid Earth can bulge as well. It's not as fluid as water, but it can move. The tidal force stretches the solid Earth by about 30 centimeters. If you just sit in your house all day, you move up and down by about that much, twice. Like the saying goes, a rising tide lifts all surfaces. The Earth...
Okay, we're done with 1 through 12 at this time. Does anybody want any repeats there? Number 12, besides water, the solid ground can also have tides, about 30 centimeters up and down. Number 6, one side of the Earth is how many kilometers closer? You know, I don't remember what that is. Did anybody get that? 13,000. Thank you very much. Number 8, the tidal force is strongest on the side facing the moon and facing away. Number 11, there are 2 high tides each day on a beach. Number 9? Number 9. High tide is when water is pulled onto shore by a high tidal force. Okay, moving on to number 13. Read that question to anticipate.
Spin has another effect. Lag in the water flow means the water can't respond instantly to the tidal force from the moon. The Earth's spin actually sweeps the bulges forward a bit along the Earth. So picture this. The bulge nearest the moon is actually a bit ahead of the Earth-Moon line. That bulge has mass. Not a lot, but some. Since it has mass, it has gravity, and that pulls on the moon. It pulls the moon forward in its orbit a bit, like pulling on a dog's leash, accelerating it. The moon responds to this tug by going into a higher orbit. The moon is actually moving away from the Earth. The rate of recession of the moon has been measured, and it's something like a few centimeters per year, roughly the same speed your fingernails grow. Now get this. The moon has gravity. Just as the bulge is pulling the moon ahead, the moon is pulling the bulge back, slowing it down. Because of friction with the rest of the Earth, this slowing of the bulge is actually slowing the rotation of the Earth itself, making the day longer.
So we're now done with 13 and 14.
The effect is small, but again, it's measurable. Okay, let's get a little change of perspective. Everything I've said about the moon's tidal effect on the Earth works the other way, too. The moon feels tides from the Earth, and they're pretty strong because the Earth is more massive and has more gravity than the moon. Just like Earth, there are two tidal bulges on the moon, one facing the Earth and one facing away. Long ago, the moon was closer to the Earth and spinning rapidly. The moon's tidal bulges didn't align with the Earth, and the Earth's gravity tugged on them, slowing the moon's spin and moving it farther away. As it moved farther away, the time it took to orbit once around the Earth increased. Its orbital period got longer. Eventually, the lengthening rotation of the moon matched how long it took to go around the Earth. When that happened, the axis of the bulges pointed right at the Earth. That's why the moon only shows one face to us. It spins once per month and goes around us once per month. If it didn't spin at all over that month, we'd see the entire lunar surface. But since it does spin once per orbit, we only ever see one face. This is called tidal locking, and it's worked on nearly every big moon in the solar system. Tides from their home planet have matched their spin and orbital period. These moons all show the same face toward their planet. Now wait a second. If the moon has gravity, which causes tides, and is the root cause behind all these shenanigans, what about the sun? It's even bigger than the moon. Tides depend on the gravity from an object and your distance from it. The sun is far more massive than the moon, but much farther away. These two effects largely cancel each other out, and when you do the math, you find the sun's tidal force on the Earth is just about half that of the moon's.
There's question 17. The next question is about spring tides, so be listening for that.
The way the sun's tidal force and the moon's tidal force interact on Earth depends on their geometry, which changes as the moon orbits us. At new moon, the Earth, moon, and sun are in a line. The moon's tidal force aligns with the sun's, reinforcing it. This means we get an extra high tide and an extra low tide on Earth. We call this the spring tide. When the moon is at first quarter, the tidal bulge from the moon is 90 degrees around from the sun's. High tide from the moon overlaps low tide from the sun. We get a slightly lower high tide and a slightly higher low tide. We call those neap tides. The pattern repeats when the moon is full. The moon, Earth, and sun fall along a line again, and we get spring tides. A week later, the moon is moved around, and we get neap tides again. Not only that, the moon orbits the Earth on an ellipse. When it's closest to us, we feel a stronger effect. If that also happens at new or full moon, we get an added kick to the spring tides. This is called the Proxygian tide and can lead to flooding in low-lying areas. Unless you live on the coast, I bet you had no idea tides were so complex. Tides are universal. They work wherever there's gravity. If two stars orbit each other, each raises a tide in the other. Just like the Earth and Moon, that can slow their spin and increase their separation. Many planets orbiting other stars may be tidally locked to those stars. Near a black hole, where the gravity is incredibly intense, the tides are so strong they would pull you like taffy into a long, thin string. Astronomers call this effect spaghettification. No, seriously, that's what we call it. Today you learned that tides are due to the changing force of gravity over distance. The strength of the tidal force from an object depends on the gravity of the object and the size of and distance to the second object. Tides raise two bulges in an object, creating two high tides and two low tides per day on Earth. Tides have slowed the Earth's rotation, moved the moon away from the Earth, and locked the moon's rotation in orbit so that the moon always has one side facing us. So, tide goes in, tide goes out. It turns out I can explain that. Now you can too. Crash Course is produced in association with PBS Digital Studios. This episode was written by me, Phil Plait. The script was edited by Blake DiPastino.
All right. Anybody have questions on 13 through 21? Number 13, the bulge of water at high tide is a bit ahead of the rotation of the moon. It pulls the moon to make it, let's see here, spin slower and get closer to Earth. No, I'm sorry. It's farther from Earth. Letter B. 15. Earth pulls on the moon in the same way as the moon pulls on the Earth. Therefore, Earth causes tides on the moon's surface. How many tides are on the moon? 2, for the exact same reason that we have 2 here on Earth. 18. Spring tide is when the moon and sun are both the same side of Earth. At this time we see extra high tides and extra low tides. Okay, for the rest of the period, you're going to work on the Riptide project. Read this here, 1 through 5. And you can watch these videos. You don't have to watch all of them, just as much as you need to understand the topic. And your task for this project is to make a safety poster. Do this in the style of a safety poster that you might see at a beach. Don't just write out the answers like a homework assignment. The requirements. Make a poster to tell people how a riptide forms. Tell people what you might see if you're standing on the beach and a riptide is present. Tell people 2 things to do to survive, have an illustration, and number 5, have your name on the front. After getting this done, let's say after completion, you will post it. I'm going to have a big piece of blue paper on that cabinet right over there. You will actually glue it onto there like those folks did on the other. This way I can't lose it. And you're going to write your name on front, let's see here, so that nobody else can claim it as theirs. And you have your name in ink, please, so that nobody can erase it and claim it as theirs.